we're now going to talk a little bit about speech perception, both the general problem and a simple case study, which we'll use as an example of how to develop theories in cognitive science using the process of rational analysis, which is sort of you can think of it as a methodological framework or a meta-scientific framework for developing theories, testing theories, and revising and improving theories of the mind. What is the problem of speech perception? It's the problem of recognizing meaningful words and word sequences from spoken language input or from signed language input, and it's really central to our ability to function as intelligent agents in the environment that we live in, because we're social agents. We communicate with each other using language, and it's really, if you think about it, it's central to our what we've achieved individually and collectively in terms of operating as an intelligent species. An example of it, so here's an acoustic waveform. This is actually a word. You may or may not recognize what word this is, but this will go into somebody's ear, a listener's ear, and the mind of the listener will do something amazing to it if they know the language. They will transform it automatically without conscious effort into a meaningful sequence of discrete symbolic sounds. And in this case, these are coherent sound sequences that cohere into a single word that has meaning. This is the word above. You probably didn't recognize the waveform, but this is actually one continuous waveform manifestation of that word above. Now, once again, I want to emphasize that this general process, as far as we know, is really not done in any robust or as generalized way in other species as far as we know. So other species, moths, for example, have extraordinary powers of hearing. They don't do anything like this. Songbirds do have extremely sophisticated acoustic patterning of their songs, but as far as we know, they don't form into these meaningful sequences that range over thousands of words, and words can be put together. And once again, our primate relatives also don't do this as far as we know. Now, this problem, like so many things in human language, we're extraordinarily good at solving it. We hear or see, if we're sign language speakers, thousands, tens of thousands of words a day. And we effortlessly, without any conscious effort, identify what they are, translate them into meaning, and interpret them, and use what the speaker is saying to guide our subsequent actions and decisions at a moment-by-moment level. But this problem is much harder than everyday experience suggests. This is why there's an entire industry of automated speech recognition software development. It's because, although there's been a lot of progress, it's a very hard problem. And even the best systems today are really still not as good as humans. So to give you a bit of a deeper understanding of how this problem might be challenging, more so than everyday experience might suggest, even for the most intelligent of agents, I'm going to give you some example recordings and ask you, what do you think is being said? What are the word sequences? And these are picked out to illustrate any of a number of interesting examples and challenges. So here's the first one. It's not easy to recognize speech. That's actually a very famous example in the speech recognition literature, so you might have heard this. It's not easy to recognize speech. But actually what I said, this was my recording, is it's not easy to recognize speech. Here's the second example.
Phil and Mary are young cousins.
You might have heard Phil and Mary are young cousins, or you might have heard Phil and Mary are our young cousins. In fact, this is an example that was constructed to be manipulable in systematic ways to push around your interpretation of what you might have heard, and we'll look at this later on as well in more detail. And our third example,
Laurel.
This is something that you might have heard before. This is actually a very famous example that went viral recently, and you might have heard Yanny, you might have heard Laurel. And in fact, different people tend to hear different versions of this, very different things, and in fact, it may depend on the speaker that you're listening to the sound with. And I'm going to leave this as a mystery, but we'll go back to it in the class and discuss in greater detail. This is a pretty amazing example. So these are three examples. Now, as I said, computer speech recognition is really impressive. These days, we can actually reliably use it for all sorts of commands. For example, we can speak simple commands to our iPhones. In fact, there's built-in software to the recording software that I'm using right now that will actually automatically transcribe what I say. But if you were to go look at the automatic auto-transcribed captions, you would immediately recognize this is still a very, very hard problem. And I encourage you to actually go and play around with the Google Cloud Speech API. This is something that's freely available, and just try some of these things out just to see what's easy and hard. And we'll do some of this interactively in the class. Now, what we're going to do is we're going to zoom in on a minimal problem in speech perception. This is obviously a very difficult and very challenging problem overall. But like many complex problems and complex phenomena, we can gain traction in understanding it by zooming into a very, very simple case that illustrates something that's much simpler than the general problem, but nevertheless is a kind of fundamental problem that it has to be solved in any of a number of instances by an intelligent system that operates successfully in this kind of environment, in this case, the spoken language environment. So what I'm going to give you is I'm going to give you sounds that are one of two minimally differing underlying sound categories. And so I want you to think about I'm going to play a number of sounds in sequence, and I want you to just sort of label in your mind what each one is. So I'm going to do this right now. First is just going to be a sequence that's going to play, and I want you to maybe just take a pen and pencil out, or a pen and paper out, or maybe take a note app out, and just write down each case what syllable you hear.
Ga. Ka. Ka. Ga. 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 Ga.
Great. And now what I'm going to do is I'm going to take those examples and I'm going to arrange them on a continuum from one end that sounds the most like, you heard probably a bunch of gas and a bunch of kas. They're going to be a continuum from ga to ka. And I want you to, once again, you can label each one, but crucially, figure out where in the transition you heard it change clearly from one to the other. So here we go.
Ga. 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 Ga.
Okay, not everybody will have heard the same thing. Once again, it depends on your ears, your brain, and also the speaker that you're listening through. There were 8 sounds there, 8 syllables. I hear the transition from ga to ka around number 5, but there's a little bit of variation in this by people. So I'm now going to give you a bit more insight into the underlying difference between the sounds ga and ka, both the acoustic difference and the articulatory difference. And that's going to help you understand where the continuum comes from and set the stage for a more theoretical analysis of how we hear the differences between the sounds and how we might hear them differently in different contexts. Okay, so what we have here in this graph is what's called a sound spectrogram representation of the word die. So that's different than the raw waveform representation that we saw earlier. This, you'll notice, has a different x and y representation. So as before, the x-axis is time, but now the y-axis is not amplitude, but it's frequency. And so this is a transformation, Fourier transformation into the frequency spectrum. So what this means is that at any particular moment in time, if we take a vertical slice, as you've seen here, there may be more energy in the sound form, in the waveform, in certain frequencies than in others. Okay, and it turns out that this analysis is a very productive way of understanding what's going on in the speech signal. Okay, so what you notice is that in any one moment in time, so if we take, for example, this moment right, I'll just sort of like put it like right here. So you'll see that in some parts of the frequency spectrum, there's a lot of energy in the waveform in one's voice. So there's a lot here, there's a lot here, there's a lot here, there's a lot here. This is in the middle of the vowel, ah, the first part. So die has a diphthong, I. And in the vowel, there's a lot of, the vowels are characterized by some areas having a lot of energy in frequency space, and other areas having relatively less. For example, there's not much energy in this part. Okay, these frequencies or frequency ranges of great energy are called formants, and that's the formants and the shape and how the formants change, over time is actually the basis of the difference that we hear in vowel sounds. It's the main basis of the difference in vowel sounds. Okay. Now you'll notice that in this example, there's really not much time between, so at the very beginning, right, sort of around here, there's a burst of energy, and then immediately you're hearing the vowel. And I'm going to contrast that with another case, which is a minimally differing word, the word tie. And what I want to emphasize here is that although if you look, you can see that this waveform is very similar. So the formants in the I sound are very, very similar in what's going on between the words die and tie. What's going on before the vowel is very different. In the case of die, there was this very, very short period of time right here where the lips had released d, which creates, you can see a burst of energy. It may be clearest to see here, which is broader and different than what the formants are doing during the vowel. But there's almost no time that elapses between that burst, which is when, once again, die, the initial burst of airflow, and the actual vowel. In contrast, for the word tie, you can see that there's actually an appreciable amount of space, of time, this interval right here, where the formant hasn't really started, but the initial burst, you can see that this initial burst right here looks a lot like what was going on up here. So these two initial bursts look rather similar. They're not exactly the same. There are some other differences, but they're rather similar. But then in the case of tie, there's sort of a gap with not much going on. In the case of die, there's really not much gap at all. And that gap, the size of that gap between the initial burst, the temporal gap between the initial burst and then the initiation of the vowel, is what's called the voice onset time. And in the study of phonetics, this distinction is often thought of as a single phonetic dimension of sounds. And in particular, the distinction between three sets of sounds in English, see, three pairs of sounds, actually can be mostly reduced, not entirely, but mostly reduced to a difference in voice onset time. This includes the difference between D and T. It also includes the difference between B and P and G and K. So for example, bout and pout have a very similar phonetic relationship as die and tie and as ga and ka. So the ones on the left here are what are called the voiced stops, and the ones that are on the right are called the voiceless stops. This distinction is used in phonology, which is the study of the abstract, discrete symbolic properties of the sounds, but it has a phonetic manifestation in that the voice onset time for the voiced stops, B, D, and G, is very, very short, often more or less zero, whereas the voiceless stops, P, T, and K, have a longer voice onset time. Okay, so what we can actually do, and this is, for example, this was a master's thesis at MIT now 40 years ago, classic study. You can just ask speakers to come into the lab and have them say sounds, syllables like ga and ka, and then you can go into the sound spectrogram analysis and actually measure the duration of that interval. And if you do that over and over again, what you find is that there's some variability even for the same pronunciation of the syllable. Every time I say ga, it's going to be slightly different. Every time I say ka, it's going to be slightly different. And so there will be a distribution of this voice onset time. And this is an illustration of, for one individual speaker, their distribution of voiced versus voice onset times, voiceless versus voiced VOTs. And you can see that the voiced has an average which is much shorter. Its mode is around a little under 30 milliseconds, and the voiceless has a much higher mode around 100 milliseconds. So there's a big difference between these two. Now, you can also turn it around and you can say, what I can do is I can actually experimentally go in and I could cut and paste that silence between the initial burst and the initiation of the vowel, and what I'll get out of that is I can actually experimentally manipulate how much something sounds like a D versus how much something sounds like a T. And that experimental manipulation, cutting and pasting the silence, is the source of the ga-ka continuum. That's how you construct a continuum like the ones that I played earlier on. So experimentally, once I've created a continuum like that, I can then play those sounds to a native speaker and I can ask them what they hear. Do you hear a ga or a ka? This is a different word. It's the word dent or tent, in also a well-known study. And for the native speaker population that they looked at here, when you experimentally manipulated the voice onset time between a very short value of 4 milliseconds and a higher value all the way up to 30 to 56 milliseconds, you see that for the shortest values, people always say that it's the voiceless version, dent. And when it's the longer VOTs, people always say it's the voiceless version. tent. But in the middle, what you can see is there's this sort of intermediate space where you get something like, it looks sort of like an S-curve. Okay, and there's some crossover point around, in this case, it's probably around 30 milliseconds, we would infer, where you're equally likely to hear something as a D or a T. Okay, and that's what's called a categorization curve in speech perception. And this categorization curve is the comprehension or listening version of the production problem. It's given a sound that you heard, what do you think the sound is? What sound category do you think it is? Now, okay, so I want to now cast this in terms of the kind of probabilistic problem and the kind of probabilistic inference problem that we looked at, that we sort of talked about in general form. Now, what we looked at earlier, we looked at a discrete problem where there were different categorical options that were possible. For example, whether an object noun phrase is a pronoun or not, and whether it's postverbal or preverbal. Those are symbolic, discrete, categorical properties. In contrast, whereas the sound category, whether something is a G or a K, is a categorical property, its voice onset time is a continuous property. And now what we've got here is that we've looked in the last two slides as the sort of mirror image problems. On the one hand, on the left, we have what we can think of as the generative or forward distributional knowledge. Given the sound category or class that a speaker is producing, what will the phonetic properties be likely to be? What's the distribution of phonetic realizations of that underlying symbolic discrete sound category? Now, of course, the phonetic realization is actually a very high-dimensional thing. It's the entire acoustic waveform, but we can oversimplify dramatically and distill out an important part of that distribution, which is the single phonetic dimension of voice onset time. And you saw an example of a bimodal distribution for a particular continuum, but conditioned on each individual class, it's a unimodal distribution. For the voiced version, it's unimodal with a short average voice onset time. For the voiceless version, it's unimodal with a longer average voice onset time. That's the generative or forward distributional knowledge. But we can also think about the reversed version of this, which is the categorization curve. What are human classification behaviors? Conceptually, humans are sort of reverse listeners, are reverse engineering. What is it probably that the speaker was saying? Were they saying a G or were they saying a K? Were they saying a K? Were they saying a D or were they saying a T? So from a modeling and scientific point of view, we want to ask, as we're building the cognitive science of mind, how do we reconcile these two distributions? And this is where I'm going to bring in sort of a meta-scientific framework for developing theory of minds. And this is called rational analysis. And this is due to John Anderson. He introduced this idea around 1990, and it's been hugely influential in the development of cognitive science up to this day. It's still absolutely central to a lot of the work that we do, certainly a lot of the work that I do. The background of assumption of rational analysis is that cognitive agents that actually live today, that have emerged in the biological world, are probably very well optimized via some combination of evolution and learning to solve the everyday tasks that are important for their daily lives effectively. For us, as native speakers of a language that we use to communicate with our fellow native speakers, speaking and listening and understanding what we hear is an everyday task that is crucial to our success as the organisms that we are. And so it's quite likely that we are optimized via some combination, once again, of evolution and learning to solve the task of language understanding and, conversely, the problem of language production highly effectively. And that background assumption is important because it gives us a starting point for developing theories. If you were to just go out from scratch and try to develop a theory of what is the human mind like, think of the enormous possibility space, possible hypotheses for the way that a human mind might be organized, or human minds in general might be organized. It's enormous. What rational analysis as a framework does is it allows us a way of constraining the hypothesis space or guiding our search in the hypothesis space as scientists for trying to come up with theories of what the mind is like. And rational analysis says is start with theories that say the mind does what it needs to do very, very, very well. What does that mean in practice? This is the sequence of steps that rational analysis suggests. First, take time as a scientist to specify precisely the goals of the cognitive system. What exactly is the cognitive system that you're studying, the part of the mind, or the function of the mind, what is it trying to do? What is important for it to do? Specify that. Second, formalize a model of the environment to which the cognitive system is adapted. What is the environment in which the agent is operating, and that the particular function or system in the mind is contributing to the behavior of the organism for it? Third, make minimal assumptions regarding computational limitations. Once again, there's an enormous space of possibilities for how the mind actually goes and operationally, algorithmically solves the problems that it faces. And there are many algorithms, as you know, that exist for any problem. Some of them work really well, some of them don't work well, some of them are pathologically bad. In principle, the mind might be deploying any of an extraordinarily large number of algorithms for any of the tasks that it deals with. Rational analysis says, assume that whatever the computational problem is, in terms of solving the goal of the cognitive system in the environment the cognitive system is operating in, assume that the mind is doing it extraordinarily well and it's not appreciably limited by computational considerations. Like, it takes too much time to do the computations, take too much memory resources. It may be hard to precisely compute a particular value. Don't make any additional assumptions. Assume that the mind is solving the problem as well as it possibly could in the environment that it's in. Then, given those assumptions, derive predicted behavior, given the first three things. And then test that against empirical data. And if you match the empirical data, you're doing really well. But if you're not, then you iterate some of these steps. You have to go revisit the assumptions, something in 1 through 3. And then once you've revised something in 1 through 3, then you can derive new predicted optimal behavior, recheck it against empirical data. And that's the loop that continues, and that's a cycle of developing the cognitive science of the mind. That's what rational analysis says. So I'm going to step you through how you might do this in the problem of the simple voiced versus voiceless discrimination classification problem in speech perception. So this is this little kernel problem, extremely simple problem, but it illustrates not only a specific empirical example in this cognition and language, but also is an illustration of the broader enterprise of rational analysis and constructing theories of cognitive science in the mind. So we're going to build a generative model. That is, we assume there's some underlying structure that gives rise to data in the world. In the case of speech perception and speaking, that model is that we assume that there's an underlying sound category, a discrete thing, that manifests as this continuous speech signal. We'll call the category C and the signal S. We illustrate this here with this sort of like intuitive diagram that C is pointing to S, and so C is giving rise to S. The shading means that S is observed by the comprehender, by the agent whose behavior we're trying to model, whereas C is not shaded, it's not. There's actually a more formal interpretation of this picture that is available, but we're not going to get into it until later in the semester. This is what's called a very simple Bayes net, and we will cover Bayes nets later on. Don't worry about that at this point if you're not familiar with Bayes nets. This is a simple illustration of the generative process. Okay, next, we can use Bayesian inference to infer C from S. So if there is a conditional distribution of C and S, then we're part of the way to being able to use Bayesian inference. In particular, we can use the conditional distribution, P of C given S. Bayes' rule tells us, if we were going to invert that, we would say that we would invert P of C of S, say that P of C of S is expressed as P of S given C, which is the likelihood distribution of what any particular sound category is to be expressed as. So that's the likelihood right here. And then the second part is the prior, okay? Condition of the prior probability of P of C. And to make this work, of course, we need to specify these things. We need to specify the prior, P of C, and the likelihood at P of S given C. So where do we stand with this? First of all, let's talk about the prior. Out of context, like in the weird experimental setting like we talked about before, where people are brought into the lab and listening to sounds in isolation, we might put a uniform prior on the probability of, say, hearing D versus hearing T. It's equally likely the experimenter is going to give me a D versus give me a T. In context, when you're doing naturalistic speech perception, that prior is likely not to be uniform because it's going to be informed by what words are more or less likely to be said in particular contexts. And that's going to be a very rich point of entry for analysis bridging between the levels of what's going on at the sentence and higher discourse levels versus what's going on at the articulatory level. And that's going to set the stage for what we're going to do after this session, which is going to be studying models of word sequence probabilities. So that's the prior. What about the likelihood? So I want to draw your attention again to the sort of generative knowledge characterization that we looked at before, which is the conditional distribution of voice onset time given the sound category, sound class. And this is actually something that if you go back and think about that first experiment that I described to you, is actually giving us that information. So we're going to use these conditional distributions or these samples collected from a human native speaker to estimate those conditional probabilities. What we're going to use, and this is your first what we call parametric probability distribution family that you encounter in this class, you'll encounter more of these. We're going to approximate this sort of messy looking distribution here by simplifying and saying, well, it more or less can be characterized as a normal or what's called Gaussian distribution. So we're going to use the Gaussian distribution as a proxy for the fine detail of what's actually going on for modeling purposes. What's the Gaussian distribution? It's a two-parameter distribution, so there's an infinite set of Gaussian or normal distributions. Each one is fully specified by saying the values of two different parameters. The first one is the mean or average, which is generally we use the Greek symbol mu to specify that, and the second one is the standard deviation, sigma. And now the probability density function is given here. This is the normal probability density. And it's a complicated looking equation. What I want to emphasize here is that the probability that we have is the probability of x of a particular sample of a distribution, a particular value in the voice onset time continuum, given the mean and the standard deviation. And it's specified in the following way. It's a complicated equation, but you will come to love it and be familiar with it. The first part that I want to emphasize is there's this piece in here, which is the squared deviation from the mean. That is that the farther, this becomes an increasingly negative value, which is as you get farther from the mean. And negative is going to wind up meaning less probable, so values far from the mean are less probable than values close to the mean. The speed of drop-off is scaled by the variance, or the variance is the square of the standard deviation, so it's effectively just the standard deviation. And then the third part outside is the normalizing constant, and that just is the least important part of it, just ensures that the distribution is proper. These are some different examples of normal distributions depending on the parameters that you fit in. So for example, if you, the black line is what's called the standard normal distribution with a mean of 0 and a standard deviation of 1. If I change the mean to 2, then it just shifts it over to the right. If, in contrast, I reduce the standard deviation or variance, then it becomes a more peaked distribution. That's a variance of 0.5. And if I increase the variance or standard deviation, then it becomes a squatter, a flatter distribution. I've increased the variance to 2. Okay, now this sets us up. If we oversimplify for a moment and we just treat the likelihood distribution, P of S given C, as a Gaussian, then we can now go and proceed and do all of the inference for phonetic category interpretation using Bayesian inference that I just described. So Bayesian inference, once again, says that the conditional probability of the category given the sound is proportional to the likelihood of the sound given category times the prior on the category. Okay, so here we're going to treat this as uniform, that prior, and then the likelihood we're going to use these, for each possible category, we plug in the normal distributions, category specific mean and variance, and then we get a likelihood. For the example that I'm going to show you here, the variances of the two phonetic categories we're going to treat as being the same, but in the general case, they could be different. And in fact, as part of your P-set, I am asking you what's the behavior when you have different variances. And there's some interesting things that arise. Okay, so what are those likelihoods conditional on the two phonetic categories? So suppose I have this value here, which is a little closer to the mode for P than the mode for B. I can look up the likelihood. So the likelihood of that value given the category P is 0.0053. The likelihood given the category B is 0.0023. And I can plug this into Bayes' rule. And in the numerator, I have that likelihood, 0.0053 for P, times the prior, 1/2. And in the denominator, I have the normalizing constant. And when I do all the math, this is 0.697. And that intuitively feels probably right. This is maybe not a great exemplar of either a B or a P, but it's somewhat more likely to be a P than it is to be a B. It's closer to the average P than it is to the average B. So Bayesian inference gives you exactly that. Now, that's for one example, but I can now, as a function of the VOT, which is the input, the value S, I can now do Bayesian inference for any particular value. And it turns out that if I then map out the Bayesian conditional distribution on the category given S, given the VOT, I get this S curve. That's actually the empirical behavior of Bayesian inference. And it turns out that that actually is not a perfect quantitative fit, but it's a decent qualitative fit to the human categorization behavior. There's this large regime where people are not very sensitive. If I were to go out farther this direction, I would also see people not very sensitive. But there's this intermediate space where the small changes create a lot of sensitivity. And that S-shaped curve captures that. However, I want to point out that the story is probably not over, because different speakers turn out to have a lot of differences in their distributions of how they speak. So the upper left, for example, is the distribution that we saw, but if I look at 3 different speakers, they have very different properties. So some of them, for example, this speaker over here in the lower right, you can actually, if you look closely, they actually do some very variable things. This speaker here on the lower left, actually all of their VOTs are pretty short. So notice that we, as intelligent agents operating in our environment, interact with lots of different people. Lots of different speakers, and the speakers are different. So we have to be adaptive. So although I've created prima facie evidence for maybe Bayesian inference, this sort of characterization of the problem according to rational analysis, there's more to say. I do want to back up for a moment, and I want to point out that if we just think about the way that I approach this problem in the context of rational analysis, let's think about what I did. The goal of the speaker was to interpret the sound that they heard as a sound category and ultimately a meaningful word. The environment is this variable phonetic realization that includes experience with the environment on the part of the native speaker, gives them distributional knowledge of their environment, which we can assume that they know these conditional distributions. And third, no computational limitations. We're assuming that the speakers do rational Bayesian inference. There's actually something a little complicated under the hood. If I go back a slide, if I say that this is actually the knowledge state here, this S curve, what's the relationship between the knowledge state and a decision? And an interesting thing to point out is that actually I have to invoke the idea that people don't have a categorical change once they cross this 50-50 line to always saying B up here when you cross the 50-50 line, they don't 100% of the time say B here and 100% of the time say P here. Actually, their behavior conditioned on their knowledge state has to be a little bit more gradient and variable. And actually, an important open question in cognitive science is what's the exact source for that? For now, suffice it to say that one possible interpretation is that one sort of very basic cognitive or computational limitation that we have to build in is that people can't actually always compute the exact best behavior on the basis of this full curve. They may, for example, have to take a random sample from their posterior, and that their behavior in an individual moment best corresponds to a random sample from the posterior. And we're going to be using that a lot as a linking assumption between the conditional distribution knowledge state within a theory and the actual human behavior. We'll come back to that issue later on. Going back to this problem of interspeaker variability, what consequences does this have for how speech perception ought to work? Well, let's imagine what we call, and I also want to give bring out the idea of, sometimes this is called an ideal observer model that you talk about, an observer who has all of the relevant information and is making the best possible inferences and doing the best possible behaviors. Imagine 2 different speakers that you might be listening to. One of them has much more variable productions, that's the one with the squatter distributions, and one of them has more precise productions, once again conditioned on each individual class. That's the one with the sharper distributions, the lower variance distributions. So if I were a listener listening to either of these speakers and I knew which speaker I was listening to and I knew the differences in the speakers, what would it do? So if I sort of run Bayesian inference on the 2 different speakers as using their likelihood distributions but the same uniform prior, I get the following prediction. For the speaker whose predictions are more variable, I turn out to have a more shallow categorization curve. It doesn't shift from B to P as immediately as it does in the previous case. In contrast, the speaker who has the more precise, lower variance productions, the categorization curve turns out to be steeper. It very, very rapidly converts from a B to a P preference. And there's a really, really neat study, Clairds et al. 2008, that I have linked to on the syllabus, that tested this prediction. And what they did is experimentally, they brought in participants in the lab, and depending on the participant, each participant got randomly assigned either to listening to a whole experiment where the speaker had this bimodal but more variable set of predictions, so bimodal but high variance distribution, versus some participants got assigned to the more precise speaker condition, where there were bimodal and sharper distributions, and tested categorization. And to go back, once again, this ideal observer model, which you could get as out from the rational analysis process, makes this prediction that the participants who are listening to a more precise speaker are going to have a steeper categorization curve than the participants listening to the more variable speaker. And that, it turns out, is actually what happens. So these are on the right-hand side, these are the human performance behaviors. You can see that for the thin line is the low variance speaker. The human categorization performance behavior is it's a more steep curve than for the more variable speaker. So that's a really nice follow-on prediction. And the point here is that we actually went, and this is the way that this study worked, is that from first principles, they started out with a theory that speech recognition is effectively a Bayesian process, that the predictions come out from a pretty simple rational analysis. They took that into the lab, and they made this prediction of if you have speakers with different category conditional variances on their VOTs, then you would actually get this difference in behavior, and that's exactly what we see empirically. So that's the cycle by which we can generate new predictions, scientifically test them, in this case it's confirmed, strengthening our picture of the simple problem of speech, or the general problem of speech recognition, at least in the simple cases, as being well characterized by ideal Bayesian inference. So to sum up this speech perception case study, we covered a simple example of classification in a continuous signal setting of the individual phoneme identification problem. We covered the principle of rational analysis that allow us to construct an ideal observer model of the process. We used Bayesian inference to implement that model, and we explored a theoretical prediction of the implemented model, in particular that when you have a wider variance of the class conditional VOT distributions, you would have a shallower categorization curve than if you had a lower variance class conditional distribution. And that experimental prediction was confirmed, once again strengthening the theory.